In this video, we're going to look at how electrons are arranged in the modern model of the atom, and how this differs from the model that you would have used when you were studying GCSE chemistry. We'll look at shells, subshells, and orbitals, and different ways that you can display this information. In the next video, we'll look at why this is important and how it can be used to explain certain data. By the time you finished GCSE chemistry, you were very familiar with this model of the atom. We have a central nucleus, and then there are electrons orbiting around the outside, and those electrons are found at fixed distances, moving around orbits that we call shells. And you probably would have learned that it was really important when you were drawing an atom that you started with the first innermost shell, and you only moved to the outer shells when that inside shell was completely full. And you might have also been told that the first shell had room for 2 electrons, the second shell had room for 8, and the third shell had room for 8. Now, all of this has some basis in reality, and it's a useful starting point for us talking about atomic chemistry, but it's largely been simplified because at GCSE we only worried about the electron configuration of the first 20 elements. So there are some of those ideas that you're going to need to let go of before we can go any further. So firstly, this idea that electrons are tiny solid particles, and if you had a small enough pair of tweezers you could just grab one. Well, that's not really how we think about electrons now. We now think about electrons as clouds of charge that probably occupy a particular space. So you can say, oh, if I was looking at an atom, there's a 90% chance that I would find some charge density here. So we're not thinking about a tiny solid thing that we could grab so much as a sort of smear of charge. The second simplification is this idea that if I have a particular electron and say it's in the second shell, it will just stay there continually orbiting at the same distance from the nucleus forever and a day. We actually know that if we give an electron some more energy, then it's capable of moving to a different shell or energy level, and we call this being excited. And this is what's responsible for those characteristic colours that are given out when you do flame tests. As you excite the electrons, they move to a higher energy level, and as they go back to their ground state, they release some of that energy as light with a particular wavelength. Next on the list of things that we oversimplified at GCSE are a couple of linked concepts. So at GCSE, when you were drawing diagrams of atoms, you knew you had to start on the inside and work your way out, and you knew that you couldn't move on to a new shell until you finished the shell that you're currently in. Now, there is some truth in this, but the problem is that as the shells get bigger and bigger, we actually start breaking them up into subshells, and we break those subshells up into orbitals. We didn't use those words at GCSE, but the concept is much the same. We're still moving from the lowest energy and closest to the nucleus to the highest energy and furthest from the nucleus, but this may not mean moving on to an entirely new shell. The real rule is not that you can't start a new shell until you finish the shell you're in, but you can't start a new subshell until you've finished the subshell you're in. Now, when you're starting out with atomic chemistry, this distinction doesn't really matter, and that's why we don't make it at GCSE. Your first shell only has one subshell, so the shell and the subshell become full at the same point. But it gets more complicated when we get to the bigger shells, because we start to have a situation where the first subshell of the next shell requires less energy to fill than the last subshell of the shell you're currently in. This diagram has slightly more information than we're ready for, but what it helps you to see, if you look at about the middle of that diagram as you're going up and down, is that we've got a subshell that's labelled 4S, that is actually lower down than one on the right hand side which is labelled 3D. And what that tells you is that 4S is lower in energy than 3D, and so it's actually going to fill first. The final point on our list of concepts that were slightly oversimplified at GCSE is about the number of electrons that can fit in each shell. And really, this makes sense because this misconception arises because we haven't taught you about subshells. And so we've left you with that idea that you can't start a new shell until you finish the previous shell. So at GCSE, you were told that in the first shell there was room for 2 electrons, which is true. And in the second shell there was room for 8 electrons, which is true. And you were also told that you could put 8 electrons into the third shell before you started the fourth one, which is true. but we didn't tell you that you could start a new shell when you'd finished a subshell rather than a whole shell. So basically, there is room in the third shell for more than 8 electrons, but we're going to start the fourth shell before that third shell is full. So what we can say is that there's room in the first shell for 2 electrons, the second shell for 8 electrons, and the third shell can take 8 electrons before we start the fourth shell. So how many electrons can fit in each shell? Well, there is a mathematical rule for this, but to be honest, since you already know the numbers of electrons in the first 2 shells, it might just be easier to remember the numbers. But anyway, the mathematical rule is 2n squared, where n is the number of the shell. So shell 1, 1 squared is 1, and then 1 times 2 is 2. So shell 1 can contain 2 electrons. And if we follow this mathematical rule, we can see that shell 3 can actually hold 18 electrons. Now these shells, or you might also hear them referred to as energy levels, can be divided into a number of subshells. And those subshells can also be divided into orbitals, which we'll get onto a little bit later. Each one of those subshells has a name, S, P, D and F. So I tend to remember PDF, as in printable document format, that thing you open with Adobe. And each one of these subshells has a particular number of electrons they can hold. 2, 6, 10 and 14. Now those do sound like random numbers, but if you think of them, they're all double an odd number. So your odd numbers are 1, 3, 5, 7, and then your number of electrons in each subshell is double that. Shell 1 only contains an S subshell, so it only has room for 2 electrons. And then with each new shell, we add a new subshell. So shell 2 has the S subshell, but it also has the P subshell. And then shell 3 has S and P and D. And shell 4 has S, P, D and F. You don't really need to worry about the F subshell. In the same way that at GCSE we only looked at the electron configuration up to calcium, which was number 20, at A level we're only going to go up to an atomic number of 36. So you're never actually going to need your F subshell. You just kind of need to be aware that it exists. If we look at our periodic table, we can start to divide this up based on which subshell the element has its highest energy electron in. So if you're an element where your last electron goes into the S subshell, then you're part of the S block and you're found on the left-hand side of the periodic table. If your highest energy electron goes into the P subshell, then you're in the P block and you're on the right-hand side of the table. And then likewise, if it goes into a D subshell, you're in the D block. An incredibly common 1 or 2 mark question at the start of any of the A-level chemistry papers is asking you to write out the electron configuration of an atom or 2 atoms or an atom and an ion. This is really straightforward. So we'll start off at the very beginning. So for hydrogen, we write a big 1 for the first shell and an S to show we're talking about the S subshell, and then a superscript 1 to show that the first S subshell has a single electron in it. For helium, it's very similar, but obviously we've got 2 electrons in that subshell, so it becomes 1s2. Now with lithium, we filled our 1s subshell, so we're going to move on to the 2s subshell. So we still include that 1s2 that we already had, we've still got those electrons in the first shell, and then we've also got 2s1. Then beryllium, we're going to have 1s2 and then 2s2. For boron, 1s2, 2s2, and then of course we're going to have to spill over into 2p. So we have 2p1. Carbon is going to be 1s2, 2s2, 2p2. Nitrogen 1s2, 2s2, 2p3. Oxygen 1s2, 2s2, 2p4. Fluorine 1s2, 2s2, 2p5. And with neon we're going to fill up our 2p subshell and have 1s2, 2s2, 2p6. Hopefully that made sense, so pause the video and have a go at doing the next 5 elements yourself. So hopefully you've come up with 1s2, 2s2, 2p6, 3s1 for sodium, and then 3s2 for magnesium. With aluminium, we're starting the 3p subshell, so 1s2, 2s2, 2p6, 3s2, 3p1. Then silicon is going to have 2 electrons in the 3p subshell, and phosphorus will have 3. You're also meant to be able to recognise and use something called noble gas nomenclature. Now basically what this means is if you look at these 5 elements that we've written out the electron configuration for, they all include 1s2, 2s2, 2p6. and that is the electron configuration for a noble gas, in this instance neon. So it is possible to just replace that first chunk with neon in square brackets, and you could do this for other noble gases as well. Now it's important that you're not doing this if it's a question that asks for the full electron configuration. So when you get that little 1 marker that says, what's the electron configuration of phosphorus, then you need to write out the full thing. But say if you're answering a question like a bonding question where you're talking about the electron configuration, but you're not actually being asked to state the full thing, then it's fine for you to use this shorthand. And you may also be asked to recognise it, often in little 1 mark multiple choice questions. Now, when you get these questions that ask you to write out the full electron configuration of an atom, it's fairly typical that you'll also be asked to do an ion. So you need to be prepared for that. I would really strongly recommend that when this happens, you use a margin or something to write out the full electron configuration of the atom first, and then look at how you need to edit that to make the ion. If you do it in just one step, it's really easy to make silly mistakes. So take, for instance, this lithium here. I know that a lithium atom would have an electron configuration of 1s2, 2s1. And then to make the lithium positive ion, I need to lose a single electron. So just like you did at GCSE, when you started on the outside and worked your way in, I'm going to take that electron out of my 2s subshell. So my final answer would just be 1s2. Likewise for beryllium, I start out with 1s2, 2s2, and then I need to lose 2 electrons. So I take them out of the 2s subshell. So again, my answer would be 1s2. For oxygen and fluorine, they're forming negative ions, and that means they need to gain electrons. And they're basically going to gain electrons until their 2p subshell is full. So for each example, we would end up with 2p6. Now, this all works beautifully and straightforwardly until we get to shell 3, and this is where it starts to get complicated and there are some extra rules you need to be familiar with. Shell 3 can contain 18 electrons, and it's made up of an s subshell and a p subshell, which you're already familiar with, and a 3d subshell. Now here's the thing, the 3d subshell is actually higher in energy than the 4s subshell. And since we're always filling things in order of how high their energy is, we're actually going to need to fill that 4s subshell before 3d. This makes a little bit more sense if we look at it graphically. So you can see here, if you look on the left-hand side, we have the s subshells. And if you find 4s, then it's higher than 3p, but it's lower than 3d. And since we're filling these subshells in the order of their energy, that means we're going to fill 4s before 3d. So if we take an example like scandium, we have 1s2, 2s2, 2p6, 3s2, 3p6, and then 4s2 is going to fill before 3d1. Now, just as a point here, it doesn't actually matter whether you choose to write them this way round, because this is the way that they fill, or if you choose to write your 3's together and then your 4 at the end. Either way is credit-worthy. Just pause the video and make sure you're okay writing down the electron configuration of these 3 elements. So for potassium, we've hopefully got 1s2, 2s2, 2p6, 3s2, 3p6, and then of course we're going to start filling 4s before 3d, so it's 4s1. Then calcium is very similar, but finishing with 4s2. And then for titanium, we are going to start needing that 3d subshell. So we're going to have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d2. But of course, it doesn't matter which way round you write these last two. So if you have got it written that way round, that is also totally fine. Now that you've got your head around the idea that we're going to fill 4s first, there's one more thing we need. We fill it up first, but we also empty it first. So if you have an example like the scandium we just saw, we fill up the 4s subshell before we get started on the 3d subshell. But then when scandium forms a single positively charged ion, we don't take out that 3d electron that we put in at the end. We take one out of the 4s subshell instead. So 4s fills first, but it also empties first. And that same thing is going to be true as we look at higher shells. And then one more rule, And unofficially, we refer to this as the copper and chromium rule because those are the two main elements that you're going to encounter this with. So atoms gain additional stability from having either 5 electrons or 10 electrons in their d subshell. So if you're thinking about an atom and it should, in inverted commas, have 4 or 9 electrons in its 3d subshell, so be almost half full or almost totally full, then what happens is that an electron moves from the 4s subshell to the 3d subshell. So if we look at vanadium, this is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d3. Fine. If we look at our next element along, which is chromium, we would expect it to be 4s2, 3d4, but that's not what happens. Instead, chromium only has a single electron in its 4s subshell, and that allows it to top the 3d up to 5. And the exact same thing happens with copper, which instead of having 4s2, 3d9, has 4s1, 3d10. Okay, so let's have a look at some exam questions, mainly just so you see how these sort of things are going to be phrased. So you could be asked to use the periodic table to deduce the full electron configuration of an element. Now, just to point out, the fact that they've said full electron configuration, that is your clue that you're not allowed to use noble gas nomenclature. They will always put it in the question, but basically these questions where they're asking you for electron config, you do need to write the full thing. So we've actually just mentioned potassium, and so we know that it's going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, because that 4s is going to fill before 3d. Then our next question, again, they're mentioning to us a full electron configuration, and in this instance we've got an atom and an ion, which is pretty typical. So for our atom, we've got 1s2, 2s2, 2p6, 3s2, 3p2. And then for chromium, we're going to start off thinking about what the atom would be. So we've just said this is one of our special examples where we've got 4s1 to allow us to have 3d5. And then if it's a 3 plus ion, we're going to need to lose 3 electrons. So the first one that we're going to lose is going to come out of that 4s subshell, because as we know, it fills first, but it also empties first. And then we're going to lose a further 2 from 3d. So we're going to finish with 3d3. Now, you don't actually need to put a little space there, you can just write it out in full. But as I say, I usually write out the full atom and then do some crossing out and rewrite. Then lastly, we're going to write the full electron config for a sulfide ion and an iron. So for sulfur, our atomic electron configuration would finish 3p4, but as we know, to get this 2- charge, the sulfide ion is going to have 2 additional electrons. So we're going to finish with 3p6. And likewise for iron, we would have 4s2, 3d6 at the end, but we're going to lose 3 electrons, firstly 2 out of our 4s, and then 1 from our 3d, so we finish with 3d5. Now, this is a slightly different question in that it's an applied question. So rather than just asking you to state the electron configuration, it's asking you to think about how you would use this. And it's also quite a nice example of where noble gas nomenclature is used within a question. So here we've got element J, which forms a nitrate with the formula JNO3-2. Now you are supposed to know the formula and the charge of a nitrate ion, so you should know that it's NO3 and then a single minus charge. And therefore, if it takes 2 of those to form a neutral compound with J, J must be forming 2 plus ions. So if we then look at our different options that are available, this one that's neon 3s1, that would be sodium. And we know that sodium is not going to produce 2 plus ions. Whereas this next one here is magnesium, which does produce 2 plus ions because it's in group 2. And then we've also got aluminium and we've also got silicon. So out of those, we know that the one that makes 2 plus ions is magnesium. So our correct answer is going to be B. Finally, in this section, we need to talk about dividing the subshells into orbitals. So as we mentioned at the start, we no longer think of electrons as physical particles, but as clouds of negative charge. And so the space that negative charge fills up, that volume, is called its atomic orbital. Now each orbital has room for 2 electrons, But as we know, all electrons are negatively charged, and therefore all electrons are repelling each other. So you're not going to completely fill an orbital before moving on. In fact, you're going to do the opposite. You're going to put one electron in every orbital that's available at a single energy level. And then once every orbital is occupied by a single electron, at that point we're going to go back and start pairing them up. Knowing about these orbitals is going to help us to explain some data about something called first ionization enthalpy, which is basically how easy or hard it is to remove electrons from atoms to make single positively charged ions. So if each orbital can hold 2 electrons, then how many orbitals are there in each shell? Hopefully you realise that shell 1 with 2 electrons only needs 1 orbital, and then shell 2 with 8 electrons needs 4, and shell 3 with 18 electrons needs 9 orbitals. These orbitals have characteristic shapes. S orbitals are shaped like a sphere, and then the p orbitals are shaped, sometimes they say like dumbbells, but basically like this. And then when you get to your d orbitals, they look a little bit like a butterfly. You're not going to be expected to be able to draw these, but you do need to be able to recognise what they are. When you're placing electrons in orbitals, you're never going to put 2 electrons in the same orbital until you don't have a different option. So basically, you're going to look at all of the orbitals that are at the same energy level to each other, so they're in the same subshell, and you're going to put 1 electron in each of those, and then once they each have 1 electron, then you start pairing. In this diagram, each one of these lines represents an orbital which can hold 2 electrons, and as you can see, each subshell is split into a number of orbitals which are all at the same level, so they take the same amount of energy to fill. So if we start off with hydrogen, it only has a single electron, so that obviously goes in 1s. Then helium has a second electron, and even though those electrons will repel each other and they wouldn't sort of choose to be in the same orbital, there aren't any other orbitals at that same energy level. So helium would have a second electron in here. And the reason we have the up arrow and the down arrow is to show that they have opposite spin to each other. So then we move on to lithium and we start our 2s subshell, and then beryllium also has another electron in that 2s subshell. Then we move on to P, and as we've said, we're going to put 1 electron in each separate orbital before we start pairing. So at this point we would be up to nitrogen with 7 electrons. Then when we get to oxygen, then we need to start pairing. Then we move on to our 3s subshell, then 3p, and then as we've already mentioned, 4s is lower in energy than 3d, so that's where we're going to go next, and then we move on to 3d. Thanks very much for watching, and I hope you're now feeling a little bit clearer about electron configuration. If you did find this useful, then don't forget to like and subscribe for more A-level chemistry videos coming soon.